In this video, we're going to take a look at decibels and logarithms. And we need logarithms because the definition of decibels is given in the form of logarithms. So what are logs all about? When we're talking about logs, logs are exponents. And they follow the rules of exponents. You recall from our video on doing the laws of exponents that if we have the same base and we're multiplying, we can just add the exponents. This is exactly how a slide rule works. It's actually just a ruler that adds the logarithms in order to do the multiplying. And over here, here's an example of logarithmic graph paper. Notice that stuff is all scrunched up in one end, and we're going by this first one. If it's 10, this one's going to be 100. It's going to be 10 times as much, 10 times as much as the previous, 10 times more, 10 times more, 10 times more, until we get down here to the end. So we can deal with really large quantities. And it's also convenient to graph some logarithmic functions using log paper because we can get more accurate graphs that way. Well, first of all, decibel, deci means 1/10 of, it's a tenth of a bell. It started out as a unit of sound. It turns out that the human hears logarithmically. So if we say something is twice as loud, we mean it's 10 times as much. So there you are. I put a simple little equation here because one of the problems that we're faced with is being able to solve equations where the variable is an exponent. How do we deal with that? And it turns out that if we take the logarithm of both sides, because there's a relationship between logs and exponents, if we take the logs of both sides, then I can solve the equation. So I can do a log, for example, base 10. Typically, if it's base 10, it's not written, of 2x. And of course, I have to do it to the other side as well. And there are different bases other than 10. This is base 2. I have a base. Remember what an exponent is. This is a base raised to some power. Okay, but if I take log of base 10 of both of these, since this expression here on the left is basically an exponent being raised to a power, remember that if I have a power raised to a power, then they multiply. Well, I can just take this x out of this notation and put it out here in front. So that gets it out of being an exponent here, and now I have just a multiply here. So if I divide both sides by this log 2, then my value for x is nothing more than the log of 8 divided by the log of 2. And calculators, scientific calculators, have log keys. So we'll do the log of 8. Used to be you had to look this stuff up, I think. Log 2, and we see that that evaluates to 3, and that makes sense. So our equation then becomes 2 to the third power equals 8, and of course we know that to be true. As I mentioned, there are other bases. Typically in math and science, we deal either with base 10 or more often than not the natural log, which is the ln key here on the calculator. You'll oftentimes have a log key, which is base 10, and an ln key for natural log. Natural log uses Euler's number, which is e, as a base and raises that to some value. Okay, so this is not about the math, this is about decibels. So decibels then are dealing with ratios of input power versus output power, signal gain, that sort of thing. And perhaps one of the most easy ones to understand is right there in your ham shack, assuming you have an HF radio with an S meter on it. An S meter starts at 0 and goes to 9, and then there'll be a plus 10 dB, plus 20 dB, plus 30 dB over that value of 9. And of course we have a needle that points somewhere on there. And this S meter is a relative value or indicator of the signal level that's coming in. In older HF radios, it was not calibrated. I don't know what date it started doing that, but if you have a relatively current radio, it's probably been calibrated. And the calibration that they use, I believe, is a minus 63 dB is approximately 50 microvolts. If you're using UHF, VHF, then it's more likely to be like minus 93 dB. It's a little different scale. But for HF, this will work fine. So that's about the equivalency. Your S meter is actually a microvolt meter. So decibels then are just a way of expressing powers of 10, especially since the human ear hears logarithmically and not linearly. I had no idea that was the case. In terms of signal gain, that's another place where we see that a lot in amateur radio. There's a so-called theoretical isotropic vertical radiator out here, and it has a gain of unity. And so if I were looking at an antenna that was advertised at plus 17 dB gain, that's a pretty good gain for an antenna. The more gain, the better signal response it's going to get. Signal to noise ratio is another thing measured in dB. You've got noise and signal, and that's going to be again something that's measured in dB, which to actually calculate it you're going to need to be able to manipulate logarithms, and any scientific calculator can do that. Let's see, what else can I say about them? I think that's about it. I don't know that much about it. I've told you pretty much everything I know about decibels. I've not found it necessary to do a lot of calculations, but gain or loss can be measured with decibels. So hopefully this gives you a little bit of a foundation and whets your curiosity a bit. Please feel free to add more to this or correct if I've made any mistakes here. That's what the discussion group is all about. Happy to hear from anybody about that. All right, have fun.